All right, so the last bit of tonight's homework is section 2.3. We're talking about position time graphs. Well, we worked with graphs, so what are we graphing? Well, we're graphing position, which is essentially distance, and time. So we're doing the very simplest of graphs that we can start doing in physics with position and time. Graphs are time on the x-axis, position on the y-axis. Now, what would that slope represent? Essentially, when you're graphing, remember, it's y divided by x is your slope. Well, distance divided by time equals what? It equals velocity or speed. So we are graphing speed. If you know distance and time and you can graph those two, your slope of your graph is going to be velocity or speed. Now what's the difference? Remember from section 2.2, velocity is speed with direction. You can have speed. Speed is just a number. Speed is no direction. Velocity means you have to include that direction since it's a vector quantity. Now, when we're talking about position time graphs, we have a couple things to go over. We have instantaneous position, which is your position at the particular moment at a particular instance. So it's your right at that particular moment. Hopefully the projector makes it and doesn't start to overheat. We'll point the fan at it and see what that does. Well, knocked it off for a little bit. So instantaneous positions, position at a particular instance. Now we worked on graphing last week, so now I just want to show you what a position time graph would look like. All right. You can see this is your slope. Now if you got a graph like this and you got to ask what is the velocity, remember that's the slope. So you have y2 minus y1 over x2 minus x1. So you're going to take this point and this point. Well, we wanted to figure that out real quick. Y1 or Y2 is 100 minus 0 over 5 minus 0. 100 divided by 5 is 20. So this would be 20 meters per second. Now the slope tells you a little bit about it. This is a straight line, so the slope is constant. It's not changing, which means your velocity is constant. It's not changing. This would be very similar to we're driving down the highway at the same exact speed. Now, what we could do is, that doesn't always happen. Let's say you're at a stop sign. Let's say one of the stoplights in Byron on a 14, where you're going to go from 0 to 65 in a very short amount of time. Your graph's going to look differently when you have a changing slope. Right? When you have a changing slope, you are always, when you have a changing slope, you're going to have a constant acceleration. If you have a constant acceleration, that means you're always getting faster, so your velocity is going to increase. So same type of deal, I get asked, well, how do I figure out the velocity at one point? Well, if you want to know how fast you are, you're going to draw a line tangent. Right? You're going to draw a line that is tangent to that point, and you're going to figure out the slope of that tangent line. And that will tell you the instantaneous velocity at that point. So in blue I did one there, and you can see that the velocity, since the slope is going to get greater, right, the car is going faster and faster. The green has a bigger slope than the blue, and the blue has a bigger slope than the red. Doing my best to draw tangents. So you have position, you have time, positions on the y, times on the x. Your slope is going to give you velocity. If it's a constant slope, if the slope is linear, you're going to have constant velocity. And if the slope is changing, you're going to have constant acceleration. And we will kind of work with these graphs in lab tomorrow. We're going to kind of work with the motion sensors, and you'll be able to experiment with constant velocity and constant acceleration.